So this can be defined. It is saying that in order to compare the stability of slopes under condition other than those of limiting equilibrium. So limiting equilibrium is where you have your forces being equal. Okay, so form of index is required, and the most commonly used index is the factor of safety, which is what I talked about. It is a standard we all compare and say that, okay, if I get a value of this, then my forces are at equilibrium. And so I can say that I am good to go. So let's say you do your calculation. We all are assuming to be geotechnical engineers, and we test our minds to see. I have done my analysis and I get a factor of safety to be this. You are always expecting that this value should be 1, which means you are at equilibrium state. If it is more than 1, then it means you are extremely safe. So let's say you did your calculation and you are getting less than 1. Should we stop mining? Anyone? You have done your analysis. You realize that you are getting a factor of safety. It's at limiting equilibrium, you should have this F is equal to 1, which means you are in the middle. If you have F being greater than 1, it means your slope is going to be stable. And when it is less than 1, you have instability. And so you have this. What are some of the things you can put in place, or what should we do? Should we stop mining? And if we are going to, Mr. Kwe, you were to say something. Go ahead.
I'm saying that you will not stop mining. You need to put measures in place to stabilize the failing to achieve that equilibrium to sustain your work.
Okay, good. So what are some of the things I can do? Okay, Mr. Opoku, your hand is up.
Okay, I think we still have to, if possible, increase bolting so that we can achieve more stability.
Okay, so we have to increase the bolting. We have to bolt more to prevent the sliding. What other things can we put in place to increase the stability?
You can also consider the slope angle again.
Exactly, the slope angle. Maybe it is too steep, so you have to do. But usually, when you more or less decrease the slope angle, do we gain or we lose? Who can tell us? Do we gain or lose? Let's put aside that of slope. We are taking aside the failure that may occur. Let's take that aside. But then let's come to, in terms of business, if we increase or decrease, what happens in terms of slope angles?
If your slope is steeper, I mean, you'll be able to mine more from the pits.
Okay. And that means if your angle is more or less less, is too down, let's say to a value of 45 and below, much of your deposit will end up serving as slopes, right? So we are going to lose. So it means in terms of factor of safety and this slope analysis, you have to also consider cost, what it is going to cost you to ensure. So it's kind of a trade-off. It's a very critical decision to make. So reducing the angle comes with a cost, and are you ready to bear that? But I think if that is the case, we'll go with the adage that says is that not it? We will rather look at it in the broader sense and see that, okay, if we reduce the angle, we'll be able to work and obtain this rather than maintaining and keep spending money for unbolting and other stuff, grouting and all that. And maybe sometimes dewatering, increasing your dewatering pace may also help you. That is, if you used to have one pump doing the job for you, or one sump, you may try to drill a borehole somewhere behind the pits. That may also help in the drainage. And all these things are things that one can put in place to ensure safety. So this is your factor of safety value. So let's move on. So there are four main types of failures, slope failures that usually occur. We have the wedge failure, the toppling, and circular. And then we have planar failure. Okay, the plane failures, the wedge, toppling, and circular. So these are the three main failures, slope failures that usually we have issues with. So the slope, the plane one is where you have an entire block like that. It's as if someone has just picked a knife, cutting through a slice of bread. Okay, you have a loaf of bread and you are cutting at a certain angle all through it, and then it pushes the material on top of it like that, and that is a plane. So you may end up getting a rectangular surface. And then you have the wedge. The wedge is where you have a discontinuity at a certain angle and another discontinuity, and then they meet up at the bottom, at the base of it. And this, at the end of the day, takes this material that is formed here off of it. So I have a discontinuity plane and another discontinuity plane. And these two, this is coming at a certain angle, and this is also coming at a certain angle, and then they coincide below a material, and that will just take this thing there off, and that gives you a wedge failure. Then I have a circular, which is in the form of a circle, sweeping the material as if it's a landslide. And then your last one, which is toppling, where you have a certain angle, and I think this one can occur if you have a very steep slope, and it happens that you have discontinuities in that manner. So they begin to fall off, slide, and fall on each other. Just like you having series of walls, and then you hit them and they begin to, one falls on the other in that order until they are all down. That is toppling. So plane failure are a common type of transitional failure and occur by sliding along a single plane. So just like you saw here, it's just one plane that a material slides over it. And occur by sliding along a single plane, which daylight. So when I say daylight, the daylight here is simply means the failure or the discontinuity showing its face at the cut face. So let me use this. No, let me just draw it. So I have a slope. So this slope I have here is what I call the cut face. That is what I have designed. That is the cut face. Okay, and I have a discontinuity. So this is the rest of the formation, the rock. Then I happen to get a discontinuity occurring here. If these are discontinuities, I don't need to bother. Why don't I need to bother? They are not showing their face here on the cut face, and so I am safe. They are within. But the moment they show up at the surface, for example, I have this one showing its face here, then trouble. And this is what we call the daylighting. A discontinuity showing its face at the cut phase. This is the cut phase, the design phase. So daylight in the slope phase, that is the dip of the slope, the dip of the failure plane is less than that of the slope. So usually for failure to occur in planar slope failures, you should have the dip of the plane that is going to cause the next failure should be less than the cut phase. That is one of the conditions for this type of failure to occur. And when considered in isolation, a single block may be stable. Forces imposed by unstable adjacent blocks may give rise to active or passive block failures. And then these are some of the conditions that were provided by Hook and Bray to explain some of the things per their research, some of the things they think are the conditions that satisfies a plane failure to occur. So the plane on which the sliding occurs must strike parallel or nearly parallel to the slope face, which is approximately plus or minus 20 degrees. Then I have the sliding plane must daylight. So this is one of the key things. It must show its face. If it doesn't show its face, there's that likelihood that it might not fail in the slope phase, which means that the dip of the angle, the plane, must be less than the dip. So the dip of the plane and then the dip of the slope phase. So this one must be less in order for a failure to occur. And then the dip of the sliding plane must be greater than the angle of internal friction. So if this planar failure must occur, whilst this angle here must be less than the slope face or the cut slope face you have designed, which is, let's say, your engineering purposes depicted that you should use an angle of 45. Then for planar failure to occur, I should have this angle being less than 45. And this must also be greater. The psi p must also be greater than the internal angle of friction. So if any of these is not satisfied, then we don't have this type of failure occurring. And the upper end of the sliding surface either intersects the upper surface or terminates in a tension crack. So it either results in a tension crack or it terminates at the surface. So for example, if this is the slope face, it's either I have the planar occurring at the surface like this of the slope, or it terminates at the top here, which results in a tension crack. So you see the whole of this material, if has the tendency of moving, or it will happen somewhere along the slope face, just like in the case of this particular diagram we have here. So this one like this happened at the top here, and then it swept off. So it started somewhere here like that. So this particular failure, planar failure that occurred was a serious one. It satisfied both this condition. The statement said that the upper end of it either intersects the upper slope or terminates in a tension crack. But in this case, it has cut across. So if that was my slope, it decided to happen like this, cutting at the top and then at the slope face. And that has resulted in this type of. So release surfaces that provides negligible resistances to sliding must be present in the rock mass to define the lateral boundaries of the slide. Alternatively, It means failure can occur on a sliding plane passing through the convex or the nose of a slope. So these are images that are depicting the types of failures we just discussed.